Okay, I'm just going to briefly go through question number 6, and you can see that I filled in the data in both boxes, and the data is the same, but there's a triangle number 1, if you will. Please know that the way you know that there's a triangle number 1 and a triangle number 2 is if the side opposite the given angle, so this side that is opposite the given angle, if it is smaller than the other side, so I tried to show this a lot smaller than the other side that was given, then you can have two pictures in this scenario. But let's just go ahead and find angle A by taking side A over the sine of angle A equals side C over the sine of angle C, and when you do this product and divide it by the 37, you get a ratio for the sine of angle A, and then you'll find out angle A is equal to 40.14 degrees. So I'm going to fill that in right here. Now, the other triangle over here, it has that long, let's just go ahead and draw this long side. But this side right here, I'm going to draw it for a minute. I probably should have drawn it in green. I think I will. I'll draw that side in green. So this side right here, and then I'm going to bring this side right here along. So this looks like this triangle, but in the new triangle, this side is going to move. This one right here is going to move over here. That's where it's going to be. So you see the 40 degrees that we just got for this angle right here, 40.14 degrees. This angle right here, which is my angle A in this new triangle, because here's C and here's B and here's angle A and side A, and this will be side C and this will be little b. This angle A is going to be 180 minus the 40.14 degrees, which is 139.86 degrees. From here, I just go ahead in each of these cases, I add these two up and subtract from 180, and here I'll get 124 it looks like 24 degrees. And here when I add the 139 and the 15, add them together and subtract from 180, I'll get 24.52 degrees. I just want you to know that when you go ahead with law of sines and find side B in this triangle, it's 114.71. I just like you to do that on your own. And then this one is 57.58. I'm going to talk about maybe this in class, but the bottom line is what this statement right here, it's a summary to the solutions of two sides and the angle opposite one of them. If A is less than the product of B times the sine of A, and it's kind of trying to cause that to be a right triangle, but A won't work, you can't get B times the sine of A, then it's not a complete triangle. It won't close up. If A is equal to B times the sine of A, that's like the vertical component, then you have a right triangle. This figure right here is saying that if this side is shorter than this side, if A is less than B, then you have two triangles and two different solutions. And then finally, the last statement says you only have one answer if you were given angle A and side B, but A is greater than B. There's only one picture to this scenario. Kind of interesting to look at. Not something that I want you to have to understand the theory behind all this, but it is pretty easy to understand. Up to you if you want to pursue that a little bit more. So let's now say that we want to do an application or a story of this. And we've got this picture, and we want to find the distance from Atlanta to Raleigh, North Carolina from this figure. How about if we could leave these letters as they are, and we could call Atlanta capital letter A, Raleigh capital letter R, and Memphis capital letter M. And we could go ahead and set ourselves up a box just so we're extremely careful. I think I'll put Atlanta, M, and R. Now Atlanta has an angle of 136 degrees at it. Let's make this little a, little m, and little r. Let's see, opposite capital A is little a, and that's equal to 640 miles. Opposite capital R is little r, so little r is 330 miles. Now, what I'm trying to find here in this problem is the distance from here to here, which is little m. So this is what I'm trying to find. That's my goal. But I can't use a Pythagorean theorem because this is not a right triangle. So I must solve for capital R first in this problem. So I'm going to go, let's go with 640, side A, over the sine of angle A equals side R over the sine of angle R. And I'm hoping I guess I did not do that, so that's okay. So we're going to go ahead and take this product and divide by 640. So the 330 times the sine of 136 degrees, then divide that by 640. Remember, this is not angle R. This is a ratio for the sine of angle R. So I've got to go second sine, second answer. So it goes in and it finds that angle R is, geez, I always do this to myself. Let's call it 21 degrees. 21 degrees. So with that being 21, I'll add these two up now. They add to be 157, which leaves me with 23 degrees, I think. Let's see, 10, carry the 1. Yep. And then now I can find side M. So M over the sine of 23 degrees, because that's the angle opposite it. I'm going to use the A's. 640 over the sine of 136 degrees, and I'll take this product and divide it by this. Looking to see if I can get my calculator up on the screen. I think I can. So I'm going to bring it over here. So I will take 640 times the sine of 23 degrees, and then I'll divide by the sine of 136 degrees. Oops, I think I lost my 6. I think I got it now. And find out that the distance from Atlanta to Raleigh is pretty much 360. Let's go ahead and write that down. So M is equal to 360 kilometers. I'm pretty sure this is, oh, it's miles. Sorry. So that's this solution right here. I've got 360 miles, and I was looking for that distance between Atlanta and Raleigh, the distance from Atlanta to Raleigh. All set. Law of sines is pretty doggone nice. Let's just draw a picture of this one, and we may do something like this in class. When an airplane is landing at an 8,250-foot runway, the angles of depression towards the ends of the runway are 10 degrees and 13.5 degrees. How far is the plane from the near end of the runway? Okay, so I guess this is going to be a red runway. So let's put the plane over here. Those are its wings, you know, and it's supposed to be kind of slanted, looking down. So it says the angle of depression for one end of the ends of the runway is, and my picture is not going to be great, but this is what it can cite this end right there, and it says that the angle of depression from a horizontal, I'm going to go ahead and draw a horizontal line. What that's telling me is that this right here is 13.5 degrees, because that's going to be the steeper. It's closer. The other end of the runway, the angle of depression is 10.0 degrees. And I want to know how far is the plane from the near end of the runway. So I want to know the distance from here to here. Ooh, my, oh my. From the near end of the runway. May not finish this whole thing, but in this large triangle right here, can you see that, and I might straighten up these lines a little bit now. Can you see if that one was 13.5 degrees and this one was at an angle of depression of 10 degrees, that this angle right here should be the difference, or 3.5 degrees? And you see this 10-degree angle here? Shouldn't this be a 10-degree angle here as well? Because those are alternate interior angles between parallel lines. And so if this is 3.5 and that's 10, that's 13.5, then this one right here, this angle right here is 180 minus the 13.5. So what is that? 166.5 degrees, I believe. All right, and then finally, the length of this, and I'm going to go ahead and erase this now. The length of this runway is 8,250 feet. I'm just going to tell you, and we can do a problem like this in class, but I'm just going to tell you that you need to find this side right here in this triangle. And then you're going to use this right triangle. So go ahead and finish this up for class. You're going to use this right triangle that has a 13.5 degree angle right here, I believe. And if you find this side, then you can find this side right here by using the cosine of 13.5 degrees equals that side adjacent over the hypotenuse. So I'm back to a right triangle trigonometry problem right here with this triangle. How far is the plane from the near end of the runway? You know, actually they probably want the hypotenuse, so never mind. I'm going to take that all away. They don't want us to do this. They just want us to know. See how you can read a problem and kind of mistakenly interpret it? I would say it's as the crow flies. How far is the plane from the near end of the runway? So from here to here, they just want us to find that side. So if you go and put letters on these angles and then, you know, call this little letter C, then this is called little letter A, you're looking for little letter B is all in this right triangle. So that's what we're looking for. I apologize for that.